Here's a small experiment you can try right now. Open your browser and navigate to google.com, no www. Just the bare domain. It loads fine. Now try maps.google.com. Different page, but it loads. mail.google.com. Also loads, takes you to Gmail. Now here's the question. How many servers did you just talk to? Your instinct might be 4 different servers, 1 for each name. And in a naive system, that's how it would work. Each name would be its own independently hosted thing, on its own machine, at its own address. But that's not how it works in reality, not even close. Google.com and www.google.com almost certainly reach the same set of servers, and even maps.google.com and mail.google.com, despite being genuinely different services, are probably sitting on shared infrastructure that serves many different named services at once. The names multiply. The underlying resources don't have to. The mechanism that makes this possible is called aliasing, the ability to give a single resource multiple names so that many different names all lead to the same destination. It sounds almost too simple to deserve serious attention, but the implications run surprisingly deep, and the technique shows up at every level of networked system design. Let's start with the problem that aliasing was invented to solve, because like most good ideas in systems design, it exists because something was painful without it. Imagine you're running a web service. You've registered your company.com and you're hosting your website on a server at some IP address, let's say 203.0.113.42. You've put that address into your DNS record and your company.com resolves to it. Everything works. Now over time, you accumulate naming commitments. You want www.yourcompany.com to also work, because users type www out of habit and you don't want them hitting an error. You've built a developer portal at developers.yourcompany.com. Your support team gave out help.yourcompany.com in 100 emails. Each of these names currently points directly to the same IP address. Every single DNS record says the same thing: go to this address. Now your infrastructure team tells you that the server is moving. The IP address is changing. Maybe you're migrating to a cloud provider. Maybe you're changing data centers. Whatever the reason, 203.0.113.42 is going away. What do you have to do? You have to update every single DNS record. Every one. Yourcompany.com, www.yourcompany.com, developers.yourcompany.com. Each one is pointing directly at the old address. Each one has to be individually found and changed. Miss one, and that name stops working. Get the update timing wrong on any of them, and you have partial outages. It's tedious, error-prone, and fundamentally fragile, because you've encoded the same piece of information, the IP address, in dozens of different places. Change the information, and you have to chase it across every place it's written. This is a general principle in system design. When the same information appears in multiple places, any change to that information requires multiple coordinated updates. The system becomes brittle. The chance of inconsistency grows with the number of copies. Aliasing is the solution. Instead of pointing every name directly at the address, you designate one name as the canonical name, the real, authoritative primary name for the resource. Then all the other names become aliases. They point not at the address, but at the canonical name. Now when the IP address changes, you update exactly one record, the canonical name's address. All the aliases still point to the canonical name. The canonical name now points to the new address. Everything follows automatically. One change, everywhere updated. That's the power of indirection. In DNS, this mechanism is implemented through a specific record type called a CNAME record, which stands for canonical name record. It's worth understanding exactly how it works, because the mechanics matter. In DNS, when you want to map a name directly to an IP address, you use what's called an A record, or quadruple A record, for IPv6. An A record simply says, this name maps to this IP address. That's the direct mapping. That's the canonical record. A CNAME record says something different. It says, this name is an alias for another name. To find the address, go look up that other name instead. Let's make this concrete. Suppose your company.com has an A record pointing to 203.0.113.42. That's the canonical name, the one with the actual address. Now you create a CNAME record for www.yourcompany.com that points to yourcompany.com. You're saying www.yourcompany.com is just an alias. Its real name is yourcompany.com. Go look that up. Now, when someone resolves www.yourcompany.com, their resolver gets back the CNAME record saying, actually, go look up yourcompany.com. So it does, and gets back 203.0.113.42. When the IP address changes and you update the A record for yourcompany.com, every single alias follows automatically. The CNAME records don't need to change. This is the everyday use of aliasing, maintaining multiple names for the same web property with one canonical address that everything else points through. But let's walk through the resolution process carefully, because there's a subtlety here that matters. When a recursive resolver is resolving www.yourcompany.com and it gets back a CNAME record, it doesn't just return the CNAME to your browser and say, figure it out. It follows the chain. It sees the CNAME pointing to yourcompany.com, so it now resolves yourcompany.com. Another full DNS lookup, potentially going through the same root TLD authoritative chain if nothing is cached. Once it has the address for yourcompany.com, it returns the full resolution to your stub resolver. www.yourcompany.com is a CNAME for yourcompany.com, which is at 203.0.113.42. Your browser gets the IP address. It doesn't need to think about the CNAME. The resolution was transparent. But, and this is important, each hop in that chain takes time. If you have a CNAME pointing to another CNAME pointing to another CNAME, every link in that chain requires another lookup, potentially another round trip to an authoritative name server. In practice, DNS resolvers follow CNAME chains, but long chains introduce latency. There's also a hard rule in DNS worth knowing. You cannot have a CNAME record at the root of your domain, at the apex. You cannot make yourcompany.com itself a CNAME. Only www.yourcompany.com or developers.yourcompany.com can be CNAMEs. The root domain must have a real A record. This is a technical constraint in the DNS specification. Now let's talk about where aliasing becomes not just convenient but genuinely transformative, and that's in the context of content delivery networks and cloud services. Consider a large media company. Let's call them newsite.com. They want their images and videos to load fast for users anywhere in the world. They sign up with a content delivery network, a CDN, which has servers in hundreds of cities globally. The idea is that when a user in Bangkok requests an image from newsite.com, instead of that request traveling all the way to a data center in Virginia, it gets served from a CDN server right there in Southeast Asia. Faster, lower latency, better experience. But how does that work, technically? The user's browser requests images.newsite.com. How does it end up at a server in Bangkok? Here's how. Newsite.com sets up a CNAME record for images.newsite.com that points not to their own servers, but to a domain controlled by the CDN, something like newsite.cdn/provider.net. The CDN controls that domain. Its authoritative name server is smart. It doesn't return the same address to everyone. When a resolver in Bangkok asks what's the address for newsite.cdn/provider.net, the CDN's name server looks at where the resolver is coming from and returns the address of the nearest CDN server in Southeast Asia. When a resolver in London asks the same question, it gets back a London CDN server's address. So images.newsite.com, one name, resolves to different addresses depending on where you are in the world. The CNAME is the bridge that takes you from the customer's domain into the CDN's intelligent routing system. This is aliasing, doing real work. The news site doesn't manage server infrastructure in Bangkok. They just maintain one CNAME record, and the CDN handles everything behind it. The name images.newsite is a stable anchor that the organization controls, pointing through an alias into infrastructure that can change, scale, and shift geographically without the customer ever updating their DNS. Cloud services work the same way. When you deploy a service on AWS and you're given an address, like a cryptic string, it is AWS's canonical name for your resource in their infrastructure. You then create a CNAME in your own domain, pointing your friendly name, api.yourcompany.com, at that AWS assigned name. AWS controls what that canonical name resolves to. They can move it, rebalance it, update it. Your CNAME just follows wherever they point it. The pattern is always the same, your name pointing through an alias into infrastructure you don't directly manage but rely on. The alias is the seam between what you control and what someone else controls. Let's step back and name the deeper idea at work here, because it comes up far beyond DNS. What aliasing creates is a layer of indirection. Instead of a direct mapping from name to address, you have a chain, name to canonical name to address. Adding that extra step, that one layer of indirection, gives you flexibility. You can change what's at the end of the chain without changing the chain itself. There's a saying in computer science, usually attributed to the computer scientist David Wheeler, that goes, "All problems in computer science can be solved by another level of indirection." It's said partly as a joke, but it contains a real truth. Indirection. The idea of going through a pointer or a reference rather than directly to a thing is one of the most powerful and pervasive techniques in system design. Pointers in programming languages are indirection. Virtual memory is indirection. Load balancers are indirection. CNAME records are just one specific instance of this idea, applied to the domain name system. They all share the same basic property. By going through an extra step, you gain the ability to change what's on the other side without changing anything on the near side. Now let's talk about a specific pattern. Multiple aliases pointing to one resource. This is extremely common for large web properties. And it raises an interesting question. If all those names lead to the same server, how does the server know which name was used? Because sometimes it matters. Oldname.com should probably redirect to company.com, while www.company.com should just load the site directly. The answer is that the name used in the original request travels with the HTTP request itself in a header called the host header. When your browser connects to the server's IP address, it tells the server, "I got here by asking for www.company.com." The server can then respond appropriately, serve the page, redirect, or return an error based on which name was used. So even though many aliases point to the same IP address, the server can still distinguish between them and behave differently for each. The aliasing handles routing, getting the request to the right server. The host header handles dispatch, telling the server which of its many identities is being addressed. Aliasing also shows up in situations you might not immediately recognize as aliasing. Email is a clean example. When an organization sets up email, they publish a DNS record called an MX record, mail exchange, that says email for this domain should be delivered to this server. Often, the MX record doesn't point to an IP address directly. It points to a host name, mail.company.com, which is itself resolved to an address. That host name is, in effect, an alias for the mail infrastructure. Change the mail servers, update where mail.company.com. Your company.com points, and email routing follows automatically, without updating the MX records. In file systems, there are things called symbolic links, or symlinks. A symbolic link is a file that just says, "I'm an alias for this other path." You can have short name as a symlink to some very long, deeply nested path to actual resource. Multiple symlinks can point to the same file. Move the file, update the symlinks, and everything that used the symlink names still works. It's aliasing in a file system namespace. In programming, when you import a library with a short alias, import numpy as np, that's a naming alias. np and numpy refer to the same module. You're creating a shorter, more convenient name for something that has a canonical name. The concept travels. Wherever there are names, aliasing is available as a technique. But let's be honest about the trade-offs, because aliasing isn't pure upside. The first cost is resolution latency. Every CNAME in a chain is an additional lookup. In practice, caching reduces this. If the canonical name is cached, following a CNAME to it is fast. But in a cold cache scenario, a chain of aliases means a chain of network round trips. CDN CNAME setups, in particular, sometimes involve 2 or 3 hops before you get to an IP address. Each hop is fast individually, but they add up. The second cost is debugging complexity. When something breaks, aliasing makes it harder to trace. www.yourcompany.com doesn't work. Is it the alias itself that's broken? Is the canonical name it points to broken? Is the address that canonical name resolves to unreachable? Is the CDN the CNAME routes through having issues? Each layer of indirection is another place to check. Engineers who work with complex DN setups will tell you that chasing a CNAME chain in an outage at 2 a.m. is not a pleasant experience. The third cost is a subtle one: alias transparency. When a user visits images.newsite.com and their browser resolves it through a CNAME to a CDN domain, the user has no direct visibility into that chain. They see images.newsite.com. They don't see newsite.cdn-provider.net in their browser bar. In most cases, this is exactly what you want, but in some contexts, security audits, network diagnostics, understanding data flows, that hidden dependency is something you need to know about and reason about explicitly. And there's a fourth cost that's more organizational than technical: alias sprawl. Over time, organizations accumulate aliases the way old houses accumulate keys that nobody knows what they open. Old product names, retired campaigns, deprecate services. The DNS is full of CNAME records pointing to canonical names that themselves no longer exist or that point to decommissioned infrastructure. When something breaks mysteriously, sometimes the cause is an alias pointing somewhere it shouldn't or somewhere that's gone. Good infrastructure hygiene means auditing and cleaning up aliases regularly. But in practice, few organizations do this as rigorously as they should. Aliases are easy to create, easy to forget, and occasionally dangerous to remove because you can never be entirely sure nothing is still using a name you think is dead. So where does this leave us? Name aliasing is one of those techniques that seems like a minor convenience until you see how much of the real world depends on it. It's the mechanism that lets organizations maintain stable, friendly names while the infrastructure underneath moves and changes. It's the seam between what users see and what engineers manage. It's how CDNs route traffic geographically without users knowing. It's how cloud deployments stay flexible. At its core, it's the application of indirection to the naming layer. And like most applications of indirection, it trades a small, bounded cost for a large, compounding gain in flexibility. The name you see is not always the name the system acts on, and that gap between the alias and the canonical name is not confusion, it's architecture.